The prevailing belief among most scientists is the Big Bang theory, which stands as the leading explanation for the origins of the universe. It encompasses the creation of stars, planets, and all life on those planets, including ourselves. Despite its somewhat whimsical name, the Big Bang offers a descriptive glimpse into what might have occurred initially. The universe was condensed into a minute space smaller than a pinhead, with particles densely packed. From this minuscule point, a colossal explosion of matter ensued, known as the Big Bang. This event, occurring billions of years ago, sets the stage for the unfolding of cosmic history. However, advancements in scientific data have led to increasing contradictions with the predictions of the Big Bang theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever constructed, scientists anticipated that its observations would bolster the Big Bang theory. Regrettably, after just 1 year in space, the telescope has astounded science with its unprecedented ability to peer deep into the universe's past. The James Webb Telescope's remarkable capabilities have unveiled galaxies dating back to a time so ancient that it challenges our understanding of the universe's origins. This revelation has sparked a fervent exploration into what existed before the Big Bang. One pivotal moment in this quest occurred when astronomer Rohan Nu, working with data from the telescope, stumbled upon a galaxy dating back a mere 300 million years after the Big Bang, making it the oldest galaxy ever observed. This discovery sent shockwaves through the scientific community, underscoring the transformative potential of the James Webb Telescope. Its mission to revolutionize our comprehension of the cosmos has just begun, promising to unveil unprecedented insights into the earliest epochs of the universe's existence. This epoch, scarcely explored before, holds the key to understanding the formation of the first stars and galaxies. The telescope's findings have defied initial expectations, revealing galaxies with characteristics surpassing previous predictions. This unexpected abundance of early galaxies has ignited a flurry of scientific inquiry, challenging researchers to reconcile these observations with existing theories. As scientists grapple with these discoveries, they confront profound questions about the fundamental nature of the universe and the forces shaping its evolution. Furthermore, the James Webb Telescope's technology is revolutionary. Stationed 1.5 million kilometers away from Earth, shielded from terrestrial interference, and cooled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments designed to uncover details of the cosmic dawn never before observed. This epoch, known as cosmic dawn, occurred no more than a few hundred million years after the Big Bang, marking the period when the first stars and galaxies began to form. The process of how this unfolded remains a subject of intense study, with theories ranging from the influences of dark matter and dark energy to the interactions among starlight, gas, and dust. The telescope's observations of galaxies from cosmic dawn offer a unique opportunity for cosmologists to test their understanding of these underlying phenomena. By scrutinizing these ancient galaxies, scientists can either confirm the validity of their current models or uncover gaps in understanding that could lead to profound new discoveries. Initially, it was projected that the telescope would find only a few faint and small galaxies in its pilot investigations. However, the reality has far exceeded these expectations. The telescope's very first images of the distant universe revealed numerous galaxies with ages, sizes, and luminosities that surpassed all predictions. This unexpected bounty of early galaxies has triggered a race among astronomers to claim new records for the earliest known galaxies. Each day brings forth claims of yet another record-breaking discovery, leaving the scientific community in awe and prompting a reevaluation of our understanding of cosmic history. In the wake of the James Webb Telescope's findings, theorists and observers have scrambled to explain the existence of these unexpectedly mature early galaxies. Some speculate that flaws in the analysis of the telescope's initial observations may be responsible for these anomalous discoveries. However, the consensus remains that these findings represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic evolution. The recent revelations from the James Webb Space Telescope regarding early galaxies raise profound questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some scientists speculate whether these observations can be reconciled with existing theories, Others suggest that they might be the first indications that the universe is even more intricate and peculiar than previously imagined. At stake is nothing less than our fundamental understanding of how the orderly universe we know emerged from primordial chaos. The early findings of JWST have the potential to rewrite the opening chapters of cosmic history, shedding light not only on distant epochs and faraway galaxies, but also on the very existence of our own Milky Way galaxy. As Mark McCarran, a senior advisor for science and exploration at the European Space Agency, puts it, "You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break." The origins of JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At that time, G. Linger, then deputy director of STSI, was tasked with envisioning what would come after Hubble. Despite initial reservations, Illingworth and a small team began laying the groundwork for what would eventually become the next-generation space telescope, later renamed JWST. Unlike Hubble, which primarily observes visible light, JWST was designed to observe in the infrared spectrum, allowing it to peer much deeper into the universe. This capability is crucial for studying early galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its large and cold star-like mirror, JWST became the ideal tool for unlocking the mysteries of cosmic dawn. The need for JWST was underscored in 1995 when the Hubble Deep Field observation revealed a plethora of galaxies in what was thought to be an empty patch of sky. This discovery hinted at the richness of the early universe and reinforced the importance of a telescope capable of delving even deeper into cosmic history. After more than 2 decades of development and at a cost of around $10 billion, JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of science observations. Early programs like the Cosmic Evolution Early Release Science Survey and the GRIS Lens Amplified Survey from Space were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded predictions. The JWST observations have challenged existing notions about the early universe, revealing galaxies that defy conventional models. These unexpected discoveries underscore the importance of pushing the boundaries of scientific exploration and highlight the transformative potential of cutting-edge technologies like the James Webb Space Telescope. As scientists continue to unravel the mysteries of the cosmos, they are poised to rewrite our understanding of cosmic history and the forces that have shaped our universe into what we see today. The early observations made by the James Webb Space Telescope have astonished astronomers by revealing extremely distant galaxies. Almost immediately prior to JWST, the most distant known galaxy was GNZ 11, discovered in 2015 with a redshift of 11, corresponding to a cosmic age of about 400 million years. However, from the outset of the JWST observations, the GLASS team, led by Rohan Neu, and another independent group made a remarkable discovery. They identified a galaxy dubbed GLASS Z13 at a redshift of 13, approximately 70 million years earlier in cosmic history than GNZ 11. The rapid pace of these discoveries was facilitated by simplified techniques for estimating redshift, which, while less precise than direct measurements, provide a quick assessment of a galaxy's distance. Surprisingly, GLASS Z13 appeared unexpectedly bright and massive, already containing a stellar mass comparable to billions of suns, despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing findings. Dozens of galaxy candidates with estimated redshifts as high as 20 emerged, indicating their existence a mere 180 million years after the Big Bang. Some of these galaxies exhibited disk-like structures, a feature not expected to manifest so early in cosmic history. Furthermore, evidence emerged for galaxies comparable in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenged the predictions of the standard cosmological model, lambda CDM, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, galaxies of such size and luminosity should not have formed so early in cosmic history. The emergence of massive galaxies in the early universe presents a significant puzzle for cosmologists to comprehend. To understand this dilemma, it's essential to look at the early stages of the universe's evolution. In the first seconds after the Big Bang, the universe was a hot and dense soup of primordial particles. Over millions of years, the first stars began to form, creating the building blocks for galaxies. This process of cosmic evolution, from chaotic beginnings to the structured cosmos we observe today, is thought to have taken approximately 1 billion years. JWST observations challenge this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing numerous small protogalactic fragments merging to form larger galaxies, as predicted by current models, JWST has detected galaxies that are already sizable and luminous. Follow-up observations with instruments like the Atacama Large Millimeter Array in Chile have provided further evidence supporting the authenticity of these distant galaxies, ruling out the possibility of low redshift interlopers. These groundbreaking discoveries open new avenues for understanding the early universe and may necessitate revisions to our current cosmological models. The JWST continues to revolutionize our understanding of cosmic history, challenging our preconceptions and pushing the boundaries of astronomical exploration. The absence of detectable dust in the observations made by the Atacama Large Millimeter Array underscores the challenges faced by telescopes in confirming observations made by the advanced capabilities of the James Webb Space Telescope. As Rohan Nu noted, while JWST can follow up on its own observations, ALMA's difficulty in detecting the galaxy highlights the intricacies of confirming such discoveries. The implications of JWST observations are profound, potentially challenging the canonical lambda-CDM cosmological model and necessitating revisions. Michael B. and Cullen expressed astonishment at the results, suggesting a significant departure from our current understanding of cosmology. One controversial theory that could explain these findings is modified Newtonian dynamics, MOND, which challenges the existence of dark matter and proposes alternative explanations for observed gravitational effects. JWST observations aligning with MOND predictions intrigue proponents like Mark McLo, who sees this as further evidence supporting the theory. However, skepticism remains among some scientists, such as Jos Arapi, who highlight the challenges in reconciling MOND with existing data. Alternatively, the absence of dust in early galaxies could offer a simpler explanation for their brightness, potentially confounding efforts to accurately measure their masses. Andrea Ferrara suggests that dust may not have had enough time to form in the early universe, or it may have been expelled during galaxy formation. Charlotte Mason and her colleagues proposed that JWST may be primarily detecting the brightest young galaxies, which are easier to spot. David Spergel suggests that efficient high-mass star formation in the early universe could explain the observed brightness of these galaxies. He theorizes that early magnetic fields may have played a role in kickstarting star formation, offering a potential explanation for the rapid emergence of galaxies in the early universe. The rapid influx of scientific papers stemming from JWST's initial observations underscores the significance of these findings and the profound implications they hold for our understanding of cosmology. As scientists continue to analyze JWST data, they may uncover further insights that challenge and expand our understanding of the universe. When the first data began streaming down from the James Webb Space Telescope, astronomers were eagerly anticipating the results. Many had been working on their data analysis pipelines for years in preparation. Instead of following the traditional peer review process, which can often take months, astronomers opted to publish their findings on AR14, a website where scientific papers can be uploaded after minimal review by moderators, but well before formal peer review. This approach allowed for a new form of peer review to unfold in near real time on platforms like Twitter and other social media channels. Rohan Nu describes it as science by AR14, and the resulting frenzy of discussion was intense and surprising. Nancy Levinson, the interim director of STSI, admits underestimating the magnitude of the activity. However, there are concerns about the potential drawbacks of this rapid dissemination of findings. Klaus Pony, JWST project scientist at SSAI, notes that while the swift sharing of results allows for quick publicization and discussion, there's a risk of rushing the process. He emphasizes the importance of the gold standard of refereed peer-reviewed papers. Early calibration issues with JWST have been identified, potentially affecting some results. Nathan Adams of the University of Manchester and his colleagues found dramatic changes in redshift values for certain galaxies after recalibration. Such issues underscore the need for caution and thorough analysis. Despite these challenges, astronomers remain excited about the discoveries made by JWST.